So, we're working on Chapter 4 of our current textbook, and we're working on Newton's 3 laws. So, we've already talked about this in a previous video. You've heard there's a law of inertia. An object in motion tends to stay in motion. Once you push it, it wants to keep going, or if it's sitting still, it wants to continue to sit still. You learn the second law, which is force equals mass times acceleration. We're actually going to talk about momentum first, but we're going to review that more here in a bit. Number 3, for every force, there's an equal and opposite force. When I push with one hand on my other hand has to push equal and opposite, otherwise they move. And it all comes down to these last two. What's a force? A force is an agent of change.
Secret agent man, secret agent man, they're giving you a number and taking away your name.
Alright, so it's an agent of change, alright? One of my favorite songs. Had to get it in video somehow. So forces can lead to two conditions, alright? They can lead to a static condition or a dynamic condition. A static condition is when two forces push and no motion happens. A dynamic condition is I start to push and there's a motion. Here the forces all sum to 0. Here the forces do not sum to 0. And when forces don't sum to 0, when they don't cancel each other, a motion will occur. It makes a change happen, an agent of change. They're vectors. If I push this way, my hand goes this way. If I push this way, it goes this way. They have not only a magnitude, but a direction. And finally, we have to have free body diagrams when we talk about forces. We have to pretend that everything is a point. And every time we do a problem, we will create a free body diagram. And let's do some problems. Let's do some forces on some things. So, if I take and I hold a mass of 2 kilograms on my hand, or in this case, I'm going to use this calculator because we're going to need this. Alright? And we're going to pretend this calculator weighs 2 kilograms. We have to realize that kilograms is a unit of mass. What I want to know is how much weight I am holding. Now, we can do that by sticking with our free body diagram. If I make this a point, there is the calculator. I'm going to call it point A. So here's a free body diagram of book. Well, what's happening? Well, there's a force acting down because we're on the earth. And what's causing it not to fall? We have a force acting back up. So I'm going to name these forces on the object. I have the force of my hand. I'm going to call it F sub H. And I'm going to call it the force of G, for the force of gravity. Again, Newton's second law, force equals ma. Well, force of G is going to be the mass times the acceleration. Well, what's the acceleration on an object on the earth? That is simply gravity. So I will tell you that F of G is 2 kilograms times 9.81 meters per second squared. And I'll just call it 9.8 to make our math easier. We'll pretend we're a little higher up. 2 times 9.8, 19.6. And again, it would be kilograms per meter second squared. Well, 1 kilogram per meter second squared is a newton. And that is a unit of weight. So I can say this is 19.6 newtons. Now, when I held the calculator, did it move? No. So I know the sum of all the forces has to be 0. It was a static condition. When I sum the forces at point A, they have to equal 0. When I look in the x direction and the y direction, first of all, in the x direction, there are no forces. So in the y direction, I know that F sub H minus F sub G, because it's down, I'm calling up positive, has to equal 0. Well, I've already found that F sub G, the mass, the weight of my 2 kilogram mass, is 19.6 newtons. Simple math. We knew the forces had to be equal and opposite. So I'm holding a 2 kilogram object. If I'm going to hold it stationary, I have to exert 19.6 newtons. Now what's a Newton? A Newton's about an apple. So it takes about 20 apples for me to hold a 2 kilogram object. Again, mass never changes. If I launch this book into space, it still weighs 2 kilograms, or it still has a mass of 2 kilograms. Its weight will become 0 because in space there's no gravity. Here on the Earth, in this situation, we sum this way. So, Newtons are a mass. So, I took an example from the book and say, to stay static, what must force F be? So here's a situation. And you notice I'm using 300 newtons, 400 newtons. And you should quickly think to yourself, I can see a 3, 4, 5 triangle. Because that's the way we're going to solve this. We know that if this is going to be static, the sum of the forces in the x direction and the y direction, we're going to think in components, has to be 0. So the first thing I'm going to do is I'm going to break F down. I'm not going to leave this as F. I'm going to move the F here. I know I'm going to have an F of x portion, and I know I'm going to have a F of y portion. Alright, I can break my force into those two components. Well, that makes my life a whole lot easier. Because then I can say, well, the sum of the forces in the x direction equals 0. Well, we can tell by observation that F of x has to be 400 newtons. We know the summation of the forces in the y direction vertically has to be 0. And remember, when I put these forces in, these two forces replace F. The x and y component will make F. So then by observation we see F of y has to be 300 newtons. And if I redraw these so you can see this, off that point, and I should have made my free body diagram over here. Free body diagram. We would have had the 300 Newton force, the F of y force, the 400 Newton force, and the F of x force. Those are the 4 forces acting on that point. I'll call it of the ring, because almost always they put these on a ring in books. Now, if I want to make this into a single force, we can redraw it. Well, we got 400 newtons on this, and if we think in components, but then we go 300 newtons, and I want to find force F. Well, Pythagorean theorem, or we see that this is a 3, 4, 5. This is force F, is 500 newtons. The angle here, if I call it A, is the inverse tangent of 300 newtons over 400 newtons. The units cross, or the inverse tangent of 3/4. And if I do that, I get 36.9 degrees. I'm going to call it 37 degrees. So, and I know that based on this drawing then, that it has to be acting in this quadrant, 37 degrees. A force has a magnitude and a direction. And this is a static situation. When you place these 3 forces, the 500 newtons at 37, the 3 and the 400, that ring does not move. They sum to 0. Well, then the question is, what's the net force on a ring in that situation? Is this a static situation? Do the forces sum to 0? Instead of saying they do, ask the question, do they sum to 0? Well, again, we got to break this into parts. That's your first part. Make a free body diagram and bust this into parts. So I'm going to have the ring again. Free body diagram of the ring. There's one force we can draw right away. The 966 newtons. That acts totally in the y direction. Now, what I have to do is I have to draw 2 forces for the other 2. And I'll start with the 707 newton force. I have an x component, and if this is 30, this is a complementary angle, it's on the 90, that's 60. So I have 707 cosine 60 in here, and over here I have 707 sine 60, and those are both newtons still. So I'll draw in those 2 forces. 707 cosine 60 newtons, 707 times sine 60 newtons. And again, if I erase the word ring here, I break the 500 down, and again, this is 45 there, so it's 45 here. 500 cosine 45 newtons, and 500 sine 45 newtons. just like separating velocity or acceleration into its components, we're doing the same with forces. So here I have 500 cosine 45 degrees in newtons. And I have another up force, right? 500 sine 45 degrees newtons. So I'm going to sum the forces in the x first. And I'm going to see what these two come out to be. And I got to use a calculator. I didn't prefigure this, so 707 times 60 cosine. I get 353 newtons in the right direction, or left, yeah, to the left I mean. 353.5 newtons this way. This force, 500 times 45 cosine. Oh, look at that. 353.5 newtons the other way. Those two forces are equal and opposite, so these forces do sum to 0. Now we got to check the y direction. The down force is 966 newtons down. Let's check the two. Again, 707 times 60 sine. 612.3 newtons. That's down. This is up. I had 966 labeled the wrong way. 500 sine 45. It's the same as cosine because it's 45. And again, these two forces, if I add them together, sum to 965.9. Guess what? I'm going to call that rounding error and say that these sum to 0 when I add these forces up. And again, think of it this way: negative, positive, positive. When you do the sum of these, they add up to 0. Again, we have a little rounding error. So the net force on the ring in this case is 0 newtons. This is a static condition. I got one more board, one more situation. And again, this one's a ton of work at first, you think. But then you might be able to do some simplification of it all, okay? The first thing I want you to notice when you look at a situation like this is, and the question would be, what is the net force on the ring? If you want to try to set this up, go ahead. But I want you to catch that this is 60, thus this is 30. And that's 30. What do you notice about the 500 and the 500? Two forces that are equal and opposite. They have no net effect. The other thing I want you to notice is we have a 150 and a 200. Well, again, we don't have to draw all the forces. I can do a free body diagram on ring. And the first thing I can actually do is drop those two 500s. Now, I'm going to draw it before I break it down. But the other thing I know is 150 minus 200 leaves 50 newtons. So I'm only going to draw the 50 newton force. Alright? I still have, and I've dealt with this one and this one, with 500 canceled. I still have the 120 this way. And then I still have two forces here. I have the 130 sine 45, the vertical portion, and the 130 cosine 45, the horizontal portion. So I started with 1, 2, 3, 4, 5, 6 forces, but I only had to translate 3 of them and break one of them into the x and y components. Now it's simply summing the forces in the x and y direction again. And I'm going to call up positive and right positive. So I'm going to sum the forces in the x direction. I have a positive 130 cosine 45, and I'm not going to waste time writing that. I'm going to write 130 times 45 cosine, 91.9. I'm going to call it 92 newtons to the right. And I have 120 newtons to the left. If I sum those forces, opposite directions, 92 minus 120, I get 28 newtons force to the left. Now when I sum the forces in the y, and again, I know that this is going to be the same since it's 45, that's why I picked it. I have 92 newtons up, I have 50 newtons down, I have a resultant of 42 newtons up. Now these do not sum to 0. This is a dynamic condition. The ring is going to move. I asked what the net force was. Well, 28 newtons this way, 42 newtons this way. Here's my resultant force F, Pythagorean theorem. F squared equals 42 squared plus 28 squared. Again, on my calculator, I can do this rather quickly. And as you get better at this, you can too. Raised to the 0.5 for the square root. I get 50.5 newtons for F. And I know the angle is like this. I just need to know the degrees. And I'll call it, this time I'll call it theta. Theta is the inverse tangent of 42 over 28. Opposite over adjacent. And I get 56.3 degrees, which I'll just round to 56. I'll say to the nearest degree. This is a dynamic condition because the forces didn't sum to zero. Again, this takes some practice. It takes using your X and Y components. We'll do some practice with the force table on this. Watch the video, try to understand the math. And remember, every time you do this, you must draw a free body diagram.